All right, welcome to Unit 3.1 Thermodynamics. This is part two of two. And in this video, we are focusing on how do we quantify energy transfer during a chemical or physical change. Be sure to annotate, and there are supplemental videos embedded in here. So before we get started, let's recap what we covered in part one. Remember, the goal is quantifying heat during a chemical or physical change. And we learned some laws, a thermal equilibrium law. So if things are at different temperatures and you put them together, they will reach the same temperature. And then also the law of conservation of energy, that energy cannot be created nor destroyed. So these laws sort of help ground us, and we need to keep them in the back of our mind when we're trying to quantify heat during a chemical or physical change. The equation that we learned to quantify heat during a chemical physical change is Q equals MCAT, or Q equals MC delta T, where Q is heat, M is mass, C is the specific heat capacity, and delta T is the change in temperature. In addition to learning about ways to quantify heat, we also learned about exothermic and endothermic. Remember that since energy cannot be created nor destroyed, any energy lost by the system is gained by the surroundings. And that we said was an exothermic process because energy or heat is exiting the system. And that will result in, we know we have exothermic process because the surroundings is going to feel warmer since it's gaining that heat energy. For endothermic, it's the opposite, where in that case, the energy is being transferred from the surroundings to the system. So that means surroundings is losing heat energy and the system is gaining it. And because the surroundings is losing the heat energy, its temperature, it will feel colder. So if something feels cold to the touch during a chemical physical change, we know that's endothermic, so it heat or energy into the system. Okay. Now, before we proceed any further, what we want to do is we want to talk about what actually happens during a chemical reaction. You've probably seen this video before. What I want you to do is just take notes in the space of what happens before, after, and during. Words you want to consider using are bonds. And then after watching this video, we're going to come back together. Okay, so you may remember from the video that during a chemical reaction, bonds are broken. So the bonds of the reactants are broken. So here we see that here are some reactant molecules, and we break apart their bonds. So the two oxygen atoms that are connected together, these two red dots, they become separated. The methane, I presume this is methane, with the carbon in the middle and then the hydrogens on the outside, that also gets broken apart. So you get these separate pieces. Then what happens is these separated atoms, they form bonds, so they rearrange and form new bonds, and that's what you saw in the video. In terms of energy, two things are happening. First thing is, to break bonds require energy. So if you look at where we're starting off with the reactants to the separated atoms, you notice that they're higher up, where the system has to gain energy for this to happen. So in order to break bonds, you absorb energy. On the other hand, if we take a look at the separate atoms going to the products, when the new bonds are formed, the energy is lower. So forming bonds releases energy. So breaking bonds, you absorb; forming, you release. That's something that's super important to note. Maybe a flashcardable moment. And the reason why that's important is because we can sort of utilize this information, how much energy is required to break and bonds, and how much energy is released when forming bonds, to figure out the reaction is going to be endothermic or exothermic. Okay, and that's super important because endothermic reactions are good for some things, and exothermics, like combustion reactions, are good for other things. Like we utilize combustion reactions in our engines for a reason. So with that being said, what do you think this is? Is this going to be exothermic or endothermic based on your definitions? You may need to go back and define exo or endothermic. Okay, so let's take a look. This is actually an exothermic reaction. Let's see how it is. These are called like energy profiles. So let's take a look at that. But first, let's define it. It's exothermic because more energy is released when forming bonds. So notice how this line is a lot longer. We're releasing more energy when we're forming bonds than absorbed when we broke it. So overall, there's a loss of energy because we lost more than we gained. And we can also just tell that by looking at the energy levels of the products versus the reactants. So the products are down here and the reactants are higher. So that means that the reactants have a higher energy than the products. So clearly we had to lose energy. So instead of drawing it this way, we can draw it in with sort of like this curved hump. And this is called a reaction profile. And you're going to see this a lot. This is an exothermic reaction profile. And we know that it's exothermic again because where we're starting is higher energy than where we're ending. So overall the process is losing energy. Take a look at what's on the X and Y axes. So on the y-axis, you have potential energy, and on the bottom is reaction pathway. That just means the reaction is proceeding along. And when we're doing energy profiles, the first thing we want to do is, after we draw the correct profile, is we want to label our reactant and product. So we start off with reactants. The first line is reactants. The second line is our product. The next thing I want us to focus on is the difference in energy between reactants and product. That is going to tell us whether it's exothermic or endothermic. So in this case, since the energy is being lost, we have a negative energy change. Delta H is the symbol that we use for that. That's called the enthalpy. You're going to be hearing that word a lot. So delta H is enthalpy. And at the top here, from the reactant to the very top of the hill, that's called the activation energy. We really focus on that in kinetics, but it's still important for you to know what that hump is right now. So that little hump from the reactant to the top of the hill is your activation energy. Okay, so we just saw for an exothermic reaction. And we know it's exothermic again because the reactants are higher than the products, or the products are lower than the reactants in terms of energy, because we've lost energy. I want you to try and draw one for an endothermic reaction. I want you to label the delta H and EA, activation energy, and explain. Great, so this should be your reaction profile. For an endothermic reaction, the products are higher than the reactants. This is still your delta H, the distance between the products and reactants. And the EA, or activation energy, is the distance between the top of the hill. Actually, that's a mistake there. Let me go ahead and correct that. Okay, so I just made that correction there. But anyway, so the activation energy is from the reactant all the way to the top of the hill. I drew it initially between the product and the top of the hill, and that's not correct. For the forward reaction, it goes from the reactant to the top of the hill. So, so this is what it should look like, and it's endothermic because the energy of the products is greater than that of the reactants. Remember, on the y-axis, we have potential energy. Okay, what you're going to do now is you're going to watch a video where we sort of show the how enthalpy is measured. And but before we do that, let's talk about what enthalpy is. It's sort of the change in enthalpy is equivalent to the heat loss or gain by a reaction if the reaction is occurring at constant pressure. So you can sort of, for now, think of delta H as heat energy that's lost or gained by the system, and we can measure that again by accounting for the enthalpy of the bonds broken versus the bonds formed. Each bond has its own enthalpy value. And so what you can do is, if you know the enthalpy or the energy that is required to break a bond, which is the opposite of forming the bond, you can sort of use that information to figure out, well, what's the overall amount of energy that is lost or gained in this process. And this is what this video is going to show you. It's going to show you some examples of that. So you're going to take notes in the space that's provided when watching the video, follow along. And then once you're done with the video, your next steps is sort of to summarize everything that you learned in part 1 and 2. Identify the purpose or importance of each thing, and also main ideas and concepts. So that's what summarizing means. Why is this important? What's the purpose of doing this? Some main ideas and concepts. You want to make flashcards of things to memorize, like equations or definitions, if that's helpful. You know, if you have other ways of memorizing things, use that as well, but flashcards are just the standard. And also generate questions, like maybe as you're watching this, there's something that you really don't know. You should be annotating the mess out of your packets. There should be a lot of little either thought bubbles or whatever, with clarifying questions that you have that deepen your understanding, that show that you're doing this not to complete it, but to learn it. And also, another thing you can do is modify CFUs. So maybe you want to take some CFUs and do your own version of the CFU, like make your own question. As we said, that's an important study skill. So that will be your next step here. All right, hope you found this video helpful. Have a quality day.